Magis morning, everyone. In this video, we will enrich our knowledge on chemical bonding, most specifically on covalent bonding. So we are going to describe how atoms form compounds, highlighting covalent bonding, and then distinguish bond order, bond length, and bond energy, and relate them to each other as well, and then use electronegativity values to predict the polarity of chemical bonds. Okay, so these are stepping stone topics in order for us to fully understand the properties of compounds, whether it is ionic or covalent. But for now, we focus on molecules, covalently bonded molecules. So, you already learned that covalent bonding involves the sharing of one or more pairs of electrons between atoms of non-metallic elements. So it's usually electron pairing, right? And then it occurs when the ionic bond formation is not favored in terms of energetics. Okay? So here is a picture of the bond formation between two hydrogen atoms. So this basically depicts what happens to the orbitals of hydrogen as they mix up with each other. So at a large distance, at infinite distance, there is no attraction yet, but as atoms collide, okay, as they generally do, then they have to find a pair for that one electron of theirs. So what they do is they actually form a single bond. So this is where covalent bond formation happens. So in the simulation, we get to know how the energies of bond formation or even bond breaking are being described. So in here, in the first scenario, we look at this graph from the right. So this is the energy profile diagram of the covalent bond formation in hydrogen gas or for hydrogen. So in the simulation, you were actually asked to manipulate the controls such that you will be modeling H atoms. Remember that you were asked to toggle this and then set the size to this and that. So you are actually modeling there the hydrogen molecule H2. All right. So at first, at infinite distance, there's no attraction yet, so there's no associated energy for them. But as they move on, okay, there is a sloping down of energy. So that means they have to release some of their energy. Okay, this is a point number 2. Now at point number 3, wherein the covalent bond happens, so we know that they have to give up some of their energy, so that's why there is a dip in the energy well. Okay, so that happens at a particular optimal distance between their two nuclei. So this is your internuclear distance. As for this case, it is 74 picometers for hydrogen, but it could be any other value for all the other elements. All right. So, and then what happens here at this distance is energy is released in order to form the bond. So again, chemical bond formation is exothermic. It releases energy. While if you want to break the bond, then you must supply the energy. So you must make this dip move upward or flatten out the curve. Okay, so energy must be absorbed if you want to break the bond. Okay, so the reverse process is endothermic. Now take note that the energy required to break or to form the bond is the same amount as the energy absorbed to break the bond. And we call this difference here your bond energy. All right, bond energy. So, and then again, this happens at your optimal distance from 0. So, at this particular distance, at this particular internuclear distance, okay, that is where bond formation occurs, and we call that also our bond length, that distance, 74 picometer. Okay, so maybe you could pause for a moment to absorb and to study. So what if, sir, I move the atoms closer to each other such that they will be really bumping? So there is a rapid change, rapid increase in potential energy. And what happens is that the atoms will be repelling each other. Since like charges, the positively charged nucleus of these two atoms will be repelling each other as well as their negatively charged electron cloud. Okay, remember that at this point it is the nuclei of the atoms that are attracting the negatively charged uh, electron cloud. That's why a bond happens. That's why a bond formation occurs. Okay, so the bond length again is the distance between the two nuclei. So it is determined by a balance between the following attractions of shared electrons to both nuclei, which causes a decrease in potential energy, and repulsion between both nuclei, which causes an increase in potential energy. So if you remember in the simulation, once you let the atoms form a bond with each other, there is a vibration that occurs, and if you try to look at the forces, okay, you see that it's actually interacting. There is an interplay of attractive and repulsive forces. Okay, and what makes the uh, atoms stick together is because it is held by attractive forces between the nuclei and the negatively charged electron cloud. Okay, now here is a figure detailing the different bond lengths and covalent radius for certain nonmetals. Okay? Remember that when we talk about atomic radii, we see it differently in metals and we see it differently in nonmetals. So we measure the atomic radii in terms of the distance, in terms of half the distance between their two nuclei for bonded atoms. Okay, so for example, if you want to know the atomic radius for fluorine, then you must have a diatomic fluorine molecule, okay, of the same kind. It must be of the same kind, and then you can get the distance between their nuclei, such that you can get your covalent radius or the atomic radius per se. What have you noticed with the values in the covalent radius and the internuclear distance? Can you pause for a moment and try to check whether you can have any insight or pattern? Okay, so if you've seen that the internuclear distance or the bond length is twice, almost as twice as a covalent radius, then very good. You are on the right track. Okay, so the internuclear distance is usually almost twice as that of covalent radius. For example, 72 times 2, you should have 144, okay, picometers. But 144 picometers is very near to 143, right? The same thing with fluorine. Okay, the covalent radius for the fluorine atom is 100 picometer. Again, and the internuclear distance between them is almost 200. Okay, which is basically double the covalent radius. All right. So we were talking in the objectives about bond lengths, okay, and bond orders. So I'd like you to notice what's in here. Okay, maybe look for some patterns. For example, in the single bonds, you try to look at fluorine, chlorine, bromine, and iodine as they are being bonded together by hydrogen. So if you remember, this arrangement is according to increasing atomic radii, right? So fluorine is the smallest in a column. Fluorine has the smallest, then followed by chlorine, bromine, and iodine. And you look at the values also. Okay, so it is increasing. Okay, so that means as the atomic radius in among atoms in the periodic table increases, so does their bond length. Okay, as long as you get to combine them with the same element. All right, so that's a pattern that has also been observed. Okay, atomic radii have something to do with the bond lengths. So maybe a minute or pause the video to take it in. Now we'll talk about bond energy. So again, the bond energy is the amount of energy that is released during bond formation or amount of energy needed to break a bond. Okay, so you see the dip in the energy well a while ago, or the energy profile diagram. Okay, that was our bond energy. Now, I'd like you to focus on the following table, which gives us the bond order, the average bond length, and the average bond energy. Uh, for certain elements, okay, being paired up together. So these are some possible combinations if you have carbon and oxygen, or if you have carbon and carbon, or nitrogen and nitrogen. All right? So bond order basically means the number of bonds or bonding pairs present. So for example, in this first CO, there is only one bond, so the bond order is at the first degree, or bond order number 1, or bond order 1. So if you have two bonding pairs, it's at the second degree, and then at the third bonding pair, at the third degree there are three bonding pairs. All right, so you just have to count the number of bonds. Now I'd like you to relate, okay, to focus on here. This is a bigger one, on the bond order and the average bond length and average bond energy. Okay, maybe you look at the values. Okay, as long as they are of the same set. Okay, a minute to do that. Please pause the video. Okay, so one significant thing here is that as the bond order increases, the average bond length for the same set of atoms decreases. Okay, so look at the first three examples. As bond order increases, the average bond length decreases. Okay, so it decreases, so it becomes shorter, meaning the triple bond here has the shortest bond length. Okay, the triple bond has the shortest bond length, but look at the relationship between the bond length and the average bond energy. Okay, as the bond length decreases, the average bond energy increases. So meaning, for the same types of atoms concerned, okay, the single bond has the least energy, the double bond has higher energy than the single bond, and the triple bond, which is the shortest, actually has the highest energy. Okay, so bali saya. So as the bond order increases, the average bond length decreases. But as the average bond length decreases, the average bond energy increases. Okay, so a minute to let that sink in. And you try to look at the other examples also. So these are general trends. Okay, it's not a fixed rule. There will always be exceptions. So do not be surprised later on if you find one. Next, so here is a listing of the average bond energies. And by the way, bond energies are measured in terms of kilojoules per mole of atoms. So we will discuss more on moles later on. But I'd like you to focus your attention in this one. So for single bond, so again, the arrangement, fluorine, chlorine, bromine, iodine. So if you've noticed, this is arranged according to increasing atomic radii, right? Increasing atomic radii. But look at what happens to the energy. Okay, so you see also a decreasing trend. Okay, so that means you relate it to the previous table a while ago. That means that the bigger the bond length is, or that the larger the bond length is, then the lesser will be the energy stored in that bond. Okay, and why is the energy in bonds important or significant? Because that is where we get heat, that is where we get energy. If you break down food, for example, okay, that is the chemical energy that we've been talking about in junior high and in grade school. Okay, so chemical energy is usually stored in the bonds. All right, and the same trend is observed. Okay, so those are bond energy, bond order, and bond length. Okay, so qualitative lang. But if you can have more, you can delve in more. Just feel free to hit me up and ask questions. Right. So now we'll talk about bond polarity. But before that, we need to review electronegativity. So electronegativity is basically the hunger for electrons. It's the ability of an atom in a molecule to attract electrons to itself. Okay, so as distinguished from electron affinity, electronegativity is the tendency, it's not an energy, it is a tendency of an atom to attract electrons to itself. And if you remember in the periodic table, we use the trend in electronegativity increases, okay, from bottom to top and from left to right. So that means the least electronegative element here is francium, and the most electronegative element is fluorine. All right. Now this is the Pauling scale, which is giving us the relative electronegativities of the elements. So values were assigned to make things easier, to make things more quantitative. All right. So for example, the most common one is that fluorine has the highest, which has an En value or an electronegativity value of 4. Hydrogen has 2.1, carbon has 2.5, nitrogen has 3.0. No need to memorize these values. They will be given in future exams, or they are usually given. Or even if you have mastered the trends in the periodic table, you can actually just visualize. Now, for example, between Na and F, they are very far away from each other, so they must have a very large difference in electronegativity. So meaning if you minus the electronegativity values of fluorine uh, and sodium, then you will end up with a large difference, okay, which will be helpful later on, okay, because in terms of bond polarity, the electronegativity values is actually telling us how polar the bond is. Okay, so when you say polar, there is a separation of charges. So that's why you have North Pole, South Pole, okay, or an negative pole or a positive pole. So there are two poles uh, that are happening or that are present. So in terms of bond polarity, it is a measure of how equally or unequally the electrons in any covalent bond are shared. So when you say that the bond is polar, okay, that means there is an unequal distribution of electrons in that particular bond. Meaning to say, in that bond, one atom draws the electrons nearer nearer to itself. Okay, well, for non-polar, the sharing is equal. Okay, the pull of the atoms in the on the electron pairs are the same. Right. So we usually use this table to quantify bond polarity. So remember the table or the scale we used a while ago, the electronegativity values. So if you take two atoms, just like what we did with sodium and fluorine, if you subtract them and get their absolute electronegativity difference, then we can actually classify them as being nonpolar, being polar, or being ionic. Okay, so if the electronegativity difference is less than 0.4, then we consider the bond to be nonpolar covalent. Okay, nonpolar covalent, meaning the electrons are shared equally. The electron pairs are being pulled at equal strengths between the atoms. This usually happens if, for example, you have H2 or Cl2, the same elements, so the same pull on the electron pairs. Now, if you have an electronegativity difference of 0.4 to 1.7, if it falls within that range, then we consider that bond to be a polar covalent bond. All right, a polar covalent bond, meaning there is a slight unequal distribution of electrons. So it maybe one atom is drawing the electron pairs to itself closer. So that's why you have a partial negative part or partial positive part. So that makes it a polar covalent bond. Now, if there is really a significant separation of charges, okay, so you can really see a positive end or a negative end. Okay, it falls greater than 1.7 for the En difference. So we consider that bond to be ionic. Okay, ionic bond. So same thing here. So there is actually a spectrum. Okay, there's a spectrum of classifications. So in here, so non-polar covalent bonding, the electrons are shared equally. Okay, for example, most significant in diatomic molecules, for example, Cl2, chlorine gas. Okay, so electrons are being shared here equally. Okay, Well, for polar covalent bonding, maybe one atom is more electronegative than the other. So if you find the electronegativity difference, if it falls between 0.4 and 1.7, then we consider it to be polar covalent. Okay? And then if electrons are transferred and you see charges really, so we consider that bonding to be ionic already. All right? So this is actually a spectrum, okay, of ionic character. Right? So for example, in determining bond polarity of En values, so if you use the polar arrow to indicate the polarity of each bond, so for here NH, FN, ICL, you are going to draw to where the electrons are most attracted to. Okay? In letter B, you are going to rank the bonds according to increasing polarity. So HN, HO, HC. So I'll give you a minute to think about that. Okay, in here, you have the electronegativity values of nitrogen or of the elements involved. So the arrow is drawn towards the atom which is more electronegative. Okay, so from hydrogen, this becomes partially positive. That's why you have this end. And the electrons will be drawn nearer to nitrogen. Okay, because nitrogen has higher electronegativity than hydrogen. Okay, the same thing with fluorine, between fluorine and nitrogen. Okay, the direction of the arrow goes to where fluorine is. Okay, and for I and Cl, so Cl is more electronegative here, and then I is 2.5, so in this end it becomes partially positive. All right. So for letter D, in order of increasing electronegativity, so if you just try to look at the trend C and O, again the trend for electronegativity increases from right or from left to right. So meaning C and O are arranged according to increasing electronegativity. And then they are all paired up with hydrogen, if you've noticed. So we have this answer. Okay, the most polar bond belongs to the HO. All right, HO. So a minute, please pause for the answers to sink in. All right. So that ends our learning targets for this morning. Now, why is bond polarity important? Because this is actually a springboard to the next topics, which is molecular geometry and molecular polarity. Okay, so there are two main features or two main important considerations in order to determine whether a molecule will be polar or non-polar. And that is if those are the polarity of the bonds and the geometry of the molecule. So we can only get the correct geometry if we are able to provide the correct lead structure, and we are able to identify whether the bonds present are polar or non-polar. All right. So this is how science works. The topics are building up on each other. Okay. So previous knowledge is actually being used, and then our goal here is to uh, actually explain the properties of compounds and of materials in general based on those scaffolded concepts. All right. So later on, we can talk about their properties, why they have low melting points or high melting points, and actually that has something to do with molecular geom and molecular polarity. Most of the properties. Okay. So that's it for today. You can hit me up with your questions if you have. I hope it has been clear, and I hope it has been a meaningful discussion. So thank you very much for listening.